Hi guys, so now that we're hopefully comfortable with equilibrium, we can talk about what happens when something changes and equilibrium is messed up. So Le Chatelier's principle talks about things that can be considered stressful to a chemical reaction, and how that reaction can shift in order to minimize the stress. So basically, reactions want to be in equilibrium, and if something happens to mess up the equilibrium, the reaction is going to do something to get back to a state of equal rates and constant concentrations. Okay, so let's look at this reaction we have here. Now, concentration is one thing that we can change to stress out a reaction. We can either add more of one of the reactants or one of the products, or we can remove some of the reactants or some of the products. Either way, you're changing concentration. So you're going to make this reaction shift in order to get back to normal, to undo the stress. So, what I mean by shift is go to the right a little bit faster. So for a little while, the forward reaction will go faster than the reverse one, or shift to the left where our reverse reaction goes a little bit faster than our forward one. And this only happens for a little while until eventually everything evens out. So let's see. The first stress given this reaction in equilibrium is to increase the concentration of H2. So I'm going to take an arrow and draw it above H2. Now, if the stress is that I increased H2, the reaction wants to shift in the direction that will make the amount of H2 go down. You're always trying to undo whatever this stress is. So think about it conceptually. Which way is going to make the amount of H2 go down? Going to the right or going to the left? Now, if I go to the right, my N2 and my H2 are combining to make NH3. So as I go to the right, if reactants are turning into products, what's happening to my amount of reactants? They're going down. So does that fix the fact that I increased H2? Yes. It makes going to the right makes H2 go down. If I were to go to the left, I would be doing the reverse reaction. I would be taking these ammonia molecules and I'd be breaking them apart and turning them into H2 and N2. So if I'm literally turning ammonia into H2 and N2, what's happening to my amount of H2? It would go up even more, which is adding to the stress. So you always want to choose the direction that's going to make that stress go away. Okay, so in this case, if I increase H2, shifting to the right would make my H2 go down. Now, whatever side you're shifting towards is going to increase. My products are going to go up, and whatever side you're shifting away from, that side is going to go down. If I'm going right, reactants are turning into products. So my reactants go down, my products go up in concentration. Now, notice this is proof that we're not in equilibrium, because if we were in equilibrium, these concentrations right here would be staying constant. But shifting to the right means that the forward reaction is faster for a little while. Okay, now let's look at my next example, decrease NH3. So now I'm going to take ammonia and I'm going to remove some of it from the container. So if I'm removing ammonia, and that's the stress, what does the reaction want to do to fix that stress or undo that stress? It wants to make ammonia go back up. So which way, to the right or to the left, is going to make ammonia go back up? What do you think? Right. If I go to the right, that means I'm doing the forward reaction. I'm taking N2 and H2 and I'm turning them into ammonia, meaning my ammonia will go up and my reactants will go down. Okay? Now, I would love for you guys to understand this conceptually, and I think you will, but a way to kind of check yourself. You're probably wondering why I have Superman in the corner over here. So if you've ever watched Superman, like in the beginning part when they play the song and everything, we say Superman flies up, 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 and away. So up and away, what's the opposite of up? Down. And what's the opposite of away? Towards. Okay. Now, I don't want you guys to write this next part down because your paper's going to look a mess. I'll write it down for you, and I just want you to watch. Okay. So what you can do to make sure you chose the correct direction is you can say, all right, whatever the stress is. So let's look at the first example. If I increase H2, you'd want to find H2 in the reaction and you'd want to put an up arrow towards it. Up goes with away. So if my stress is an up stress, I want to look at the equilibrium arrows and pick the one that's facing away from this stress. So which one of these arrows is facing away from this? The right. If I'm going to the right, I'm going away from my stress. Okay? You'll do the same thing, guys, if it's a downward stress. So for the second example, it says I'm decreasing NH3. So this time I want to find NH3 and I want to put a down arrow because I'm decreasing. If you have a down stress, your equilibrium should face towards it. So if this is my stress, which one of these arrows faces towards that stress? Going to the right. So again, I would love if conceptually you understand this, but you can use your up and away, down and towards always to check yourself. Okay? All right, so concentration is one stress, and that's how we deal with it. Temperature is another thing we can do to stress out a reaction. So conceptually, to talk about this specific reaction, I see that energy is written over here on the right side, meaning my forward reaction is exothermic, energy is being released, and my reverse reaction is endothermic. I'm absorbing energy to go back in the other direction. Okay. Now I want you guys to think about if we were doing this chemical reaction in real life. If it's an exothermic reaction, that means that the chemicals are releasing heat to the surroundings and to the environment. So us holding that test tube, we would feel heat. So whatever side energy on, that's your hot side of the equation. And whatever side energy is not on is your cold side of the equation. Okay, labeling this is going to help you make sense of it when we get a stress. So now, right now, this reaction is in equilibrium at a certain temperature. If I increase the temperature, that's considered a stress. The reaction is going to shift in the direction that will get rid of that extra heat. So the fact that we just labeled our hot and cold sides, which side of this equation is going to make the temperature go back down and undo my stress? Going to the left, going to the cold side. So if I'm going to the cold side, right, I'm going towards the reactants. I'm doing the reverse reaction faster than the forward one. So what's going to happen to my amount of N2 and H2? They're going to increase because they're on the left side. And my NH3 is going to decrease because it's on the right side. Okay? Same thing if I decrease temperature, guys. Decreasing temperature is also a stress. So if my reaction was in equilibrium and I just decreased temperature, the reaction would be like, wait a minute, I need temperature to go back up. I want to try to get back to normal. So which direction would we go in to make the temperature go back up? We would go towards the hot side, which is the right side. If I'm going to the right, that means I'm doing the forward reaction faster. I'm turning reactants into products. So what's happening to my amount of reactants? They're going to go down and my products are going to go up. Okay, so there's how you can do that. Anytime temperature is increased, the endothermic direction is favored. That's something that's helpful to know. And anytime you decrease temperature, the exothermic direction is favored. And we could have given you guys a reaction that was endothermic, like energy could have been written on the other side. So it is worth it to think about what side is the hot side and what side is the cold side before doing temperature as a stress. If you did not write all of this down, I want you to pause the video and write it down, because I'm going to erase the stuff above the equation really quickly to show you how you can use the trick to check yourself. But I want you to make sure you have that stuff written down. Okay, so I'm going to erase this and show you that up and away, down and towards can work here as well. So in this equation, temperature is not in this equation. Kilojoules is a form of energy, but we can pretend that temperature and energy are the same thing for the sake of checking our work. So if the first stress is increased temperature, what I want to do is the same as before. I want to find temperature in the equation, and I want to draw an up arrow above it, right? So up goes with away. Which of these arrows is facing away from this arrow? The one to the left, which is what I put. So I got that right. I can do the same thing for decreasing temperature. I could say, okay, let me find temperature. Here it is. Decreasing means I'm making the temperature go down. Up goes with away. Down goes with towards. So which of these arrows is facing towards this down stress? The right arrow. And that's what I chose. Okay. So it's a nice way to check yourself. Okay. Now with temperature, we need to be careful because with temperature, the value of K can be affected. If you're going in the forward direction quicker, you're making more products. And when you do, if you think about what the formula for K was, products divided by reactants. If you're shifting to the right, your products are going to become greater, meaning your top number is greater and your KEQ is going to go up. So we'll say if we shift to the right, K increases because your top number, your numerator, is going to be higher. Where if you're shifting to the left, your bottom number is going to get bigger. So you're going to be doing a smaller number divided by a bigger number. So your K is going to go down. So if you're asked, like, what type of stress can change the K once the reaction is back in equilibrium, temperature can actually do that. And that's how you have to figure out which way it shifts first. Okay. The last stress that we're going to talk about, guys, is a pressure stress. And unfortunately, our Superman trick does not work. It does not work with pressure. So there are a very specific amount of steps that we have to go through when we know that pressure is a stress. So the first thing I want to do is I want to only pay attention to things that are gases. So let's write gases only. This reaction happens to only have gas in it, but if it had other phases in it, you'd want to ignore those phases. So everything's a gas. Next thing I want to do is I want to count how many moles of each gas I have on each side. So nitrogen doesn't have a coefficient, meaning I have 1 mole of nitrogen and I have 3 moles of hydrogen gas. So that's a total of 4 moles of gas on this side of the arrow. On the other side of the arrow, I have a 2 in front of ammonia, so I have 2 moles of gas. Now I want you guys to think back to the pressure unit. Pressure comes from the number of collisions the particles have against the walls of the container. So which side is going to produce more pressure, the side with more gas or the side with less gas? Hopefully, you're thinking the side with more gas. This is the side where if I shift to the left, I'm going to be making more gas, so I'm going to make the pressure go up. If I shift to the right, I'm going from 4 moles of gas to only 2 moles of gas. So I'm making less gas in the container, therefore the pressure is going down. Okay, so I have to actually do all of that work before I even go ahead and read the question. Now, for the first example, they're saying, okay, my reaction was in equilibrium, and now I went ahead and messed it up by increasing the pressure. Increasing the pressure is the stress. So, what does the reaction want to do? The reaction wants to get rid of that extra pressure. It wants to make the pressure go back down. So, which way? Going to the left or going to the right is going to make the pressure go down? Going to the right. There's less gas molecules over there, so the number of collisions is going to calm down. If I go to the right, everything on the left side goes down and everything on the right side goes up. Same thing if I decrease pressure, guys. I want to be like, okay, that's stressful. What does the reaction want to do to fix itself? The reaction wants to make the pressure go back up. It wants to go back to normal. So which way is going to make the pressure go back up? Going to the left. If I go to the left, my reactants are going to increase. I'm making 4 moles of gas out of 2, more pressure, and my right side's going to go down. Okay. So that's Le Chatelier's principle. Just to summarize, things that are important to know. Everybody kind of thinks of this as going on inside of two containers, like a left one and a right one. All of these reactions are taking place inside of one beaker or one vessel, one chamber. So you're not doing something to the left side or doing something to the right side. You're messing up the whole reaction, and then it shifts to either side to kind of fix itself. So that's something that I feel like is usually imagined incorrectly. When we say shifting left, what do we mean? We're favoring the reverse reaction. Therefore, my reactants increase and my products decrease. So this is just in general. If I say that I'm shifting right, I'm favoring the forward reaction, and my reactants will decrease and products will increase. Okay. So that is it for Le Chatelier's principle. I'm going to have you guys give this a try instead of giving you questions to do in your Edpuzzle. So give this chart a try, and we will talk about this tomorrow.